I'm Sarah Nepper, one of the organizers for the Collegeville Workshop 2020 on developer productivity. And here with me is Hal Finkel from Argonne Leadership Computing Facility. He wrote a white paper on the many faces of the productivity challenge in scientific software, as you can see, and will present some of those key ideas and insights. So Hal, please take it away.
Okay, thank you, Sarah. And thank you for inviting me. I'm going to talk about some of the ideas that are key to the white paper, which will also be available. And I think the key thing that I really want to get across here is that productivity affects all phases of software development. There's a whole software development lifecycle. And when we think about programmer productivity, it's often the case that people have a more restricted view on this than I think is optimal. And it's really important that we consider all of the phases of software development when we think of productivity, because there are really important challenges in each of those phases. So to start, I want to start thinking about software productivity even before you write the first line of code. And normally, when you are thinking about developing software, you start with some concept of what you want the software to do, and then you have to translate that somehow into a design. Now, this translation process in scientific software development is unfortunately not very productive. So I say that for two reasons. One is that, in science, as in most other areas, we have to build on existing solutions, right? We need to learn from what was done in the past and improve on that for the future. But if you try and search for information in scientific software development on how problems that are similar to the problems you have were solved in the past, this is quite difficult. The search engines or using Google Scholar or something like that is obviously quite helpful, but you can't really put your mathematical equation into Google Scholar, for example, and expect it to provide some meaningful result. And searching for it on GitHub is not really all that helpful either. So it's actually a quite iterative and difficult process to try and find literature and also code that's relevant to the kind of software you need to design so that you can learn from what was done before. And I think that going forward, we definitely need to try to create systems that make that process more productive, to let you search for things, code and papers and documentation in a way that understands more about what's going on, that understands more of the mathematical structure, so that you have some hope of finding relevant past work. The other thing that goes into this design process is the capabilities that are needed for the software, the dependencies you're going to end up having. When you create software, you don't generally start from scratch in the sense that you're going to develop every capability that your software is going to need in order to run. You're going to end up using libraries and programming environments and other things that have been created by others. And it can be very difficult to plan out exactly how you're going to use these various things. I mean, first there's the issue of finding them, of course, but beyond that, it can be very difficult to figure out if a particular library is maintained, whether what its transitive set of dependencies are, on what platforms they're available, if those platforms are expected to change in the future, and so on. And so we really need some way of keeping track of that information in a more systematic manner. So that way, this planning process can be more efficient. One thing that's important here, of course, is that because this part of the process is difficult, changes often occur later in the process, which also harm productivity. The next stage in the process is the authorship process, where you now have your design, you've scoped out what libraries you think you're going to depend on, and so on. And now you need to create the actual implementation. Now, of course, this is the sort of traditional piece that people think about when they think about productivity in software development, right? This is the writing code part. And I think that there's been a lot of effort here, of course, in programming languages and systems, in creating better IDEs and static analysis tools and so on. But going forward, there are definitely opportunities to make this part of the process more productive. We're seeing in other contexts things like code editors that use artificial intelligence to uh, produce more applicable autocomplete results when typing. These things are available for languages like JavaScript and Python. Now, Python is sometimes relevant in HPC, but for a lot of scientific software development, we would need these capabilities to be available in languages like Fortran or C++. We would need capabilities that understand more about mathematical structure and can be more efficient about generating code based on the physical model of the world we're trying to represent computationally. And I think that there's a large opportunity here to create tools in this space to make that more productive. The other thing that's really important in scientific programming, especially because we end up using languages like C++, that take a long time to compile sometimes, and we have large code bases that take a long time to compile regardless of the language. This is really another area where productivity is very important. If I have to make a change and then I have to wait 20 minutes while my program recompiles before I even know if I typed the thing correctly, that's not a very productive way of programming. And unfortunately, in many applications and code bases, this is precisely the situation in which the developers find themselves. So I think that this is an area where we can create tools that will help us to refactor code to be in smaller pieces, to maintain tests that are more like unit tests, so you can compile and test things in smaller units and so on, that will really help make the development process more productive, especially in the context of large applications and frameworks. So after you write code that you think more or less works and it compiles and I suppose runs, then of course you have the challenge of actually making it right. So this is debugging, and debugging includes aspects of both verification and validation, but both are difficult, and especially in the context of high performance computing for scientific computing needs, debugging is really hard. So one, you're often in a situation where you don't have direct access to the hardware on which you need to run. You might end up even doing debugging inside of a batch scheduled system. Now, maybe there are debug queues that help with that, but still, the turnaround time can be non-trivial, and it can be very difficult to interactively see what's going on. There are some HPC-style debuggers that run across distributed memory systems, but they have their own challenges, including scaling challenges, and in addition, it can be hard to schedule a time when you can use them, right? Because that might require an interactive session, which can be hard to come by on a system that is highly contended. Once the code is debugged, then the next stage is to tune it and make it perform well. Now, I'm presenting these in this order, and of course, the reality is that you don't strictly accomplish things in this order. In development, debugging, and tuning are an iterative process. But nevertheless, tuning is another process which has productivity challenges as you look at the scientific computing space. There are certainly tools that will help you profile your code, but these tools don't often particularly tell you what to do with that information once you've collected it. The information can also be difficult to collect, and as a result, tuning of code to run with high performance often is both time-consuming and also requires specialized skills. So not every scientist, even scientists who are reasonably competent at writing code, are well versed in the techniques that are needed in order to actually tune that code to run at high performance. And I think there's a really good opportunity here to create tools tools that act more like advisors, in addition to just like profilers, that will help people tune their applications to run with high performance. Okay. The next stage I would call integration. So one thing that's true is that often applications in the scientific workflow are created in isolation. In some sense, you might think of this like the traditional Unix philosophy, but in the end, they all have to be integrated together into some kind of larger workflow. Now, what makes this difficult, especially as we look toward large sort of multi-physics applications that are running in HPC, is that the integration method has a significant effect on performance. So there are a variety of tools that are available for integrating systems together in the wild that come from industry, from the cloud, from other kinds of environments, and many of them are not really usable in this context because their overheads would be too high. They would essentially imply copying or worse, encoding and decoding large arrays in order to pass them between components, and that's just not an expense that you can bear in this kind of environment. And as a result, we have to think more carefully about how this integration is actually accomplished. But there isn't very much tooling and support available to do this. And so people end up writing a lot of this bespoke by hand over and over again in each different application context. And we could really do a better job here at supporting application development in this integration task. The other integration thing which is relevant here is resource sharing. So if you have different components, because you're worried about the performance, you really need to make sure that the system is scheduled appropriately, right? You don't want a whole bunch of different components all running a bunch of threads and having that oversubscribe the system in a way which is unhelpful. And so the different components have to share resources somehow, but we don't really have a great common language that all the components can use to share resources across different systems. And so this ends up being a particular challenge. Now, resources here can be things like threads, they can be GPUs, it can also be memory. And this is true especially if different applications have caches or side data structures. And it may be the case that you need some components to take more memory in some phases and then relinquish it to other components in other phases. And we don't really have a good common API for this. So all this ends up being bespoke. Sometimes things have to be hacked in order to get them to work together. And it's not very pretty. So this is definitely another area where we could do a better job. Another area that's kind of related to this is in provenance. So in scientific applications especially, it's really important that it's reproducible. The running, the configuration, figuring out how you built stuff, how you associate the configuration with the output from the application. And again, this is an area where we have a common set of requirements across many, many applications, but we don't really have a good system to help people keep track of this stuff. And so when it's done at all, or to the extent that it's done, I should say, we tend to have bespoke solutions where each application team or library has to develop its own way of doing this. And that's really not productive. Now, maintenance tasks. Applications live over time. The common refrain is that most software ends up exceeding its design lifetime, right? So the idea that you're going to write something and throw it away or use it only for a short period of time almost inevitably ends up being incorrect. And so you end up maintaining the software you write for likely longer than you wanted. And what happens is that the tasks of maintaining software are a place where we can really help improve developer productivity, I think much more than we already have. We really need to have better tools for refactoring, for upgrading code, for adapting to new versions of libraries and programming languages and so on. And this is a place where we we share requirements with industry and the broader community, but there definitely are circumstances in which we need tools that are specific to the kinds of libraries, for instance, that we're using. And this is an area where I think specific investments needed in the scientific and HPC space. The piece of this, which I think is important not to lose, is one thing that is involved in maintenance, of course, is that there's the aspect of time. And the other thing that changes with time is not just the code, but also the people. And so one thing that's very important as we think about productivity is how long does it take you to get a new person onto the team and working on a particular piece of software productively. So you can have the best system in the world that is highly productive for the 2 people who originally wrote it. But if it's essentially impossible for anyone else to onboard and get involved in that team because they have to learn some sort of bespoke, undocumented code generator or something, then in the end, even though you thought that was very productive, it's not going to turn out to be that way in the long term. And so it's important that across the board for all these capabilities, we have to think about how easy they are to learn so that the teams can actually get new people onto them in order to persist over time. Now, the last thing I want to highlight, I'll call knowledge transfer, which is in some sense something I could paraphrase as saying you should document your code. But this is of course essential to do maintenance and preserve scientific integrity and all sorts of other things. But it's also really important because while essentially every piece of software you write you're going to end up using for longer than you thought, it's also true that all software has a finite lifetime. And you, at some point, maybe not when you thought, but at some point you will end up needing to replace it with something else. And this is because design requirements change over time. And at some point, the evolutionary approach just won't work. And this doesn't necessarily mean this happens for whole applications all at once. Sometimes this is true for subcomponents, where you say, okay, I can't really evolve that subcomponent to meet a new requirement. I have to rewrite that component. Sometimes it does happen for whole applications. This is, of course, very expensive. But one of the things that makes it even more expensive is when you don't know what the first original component actually did. And so if you want to be able to efficiently replace things when you need to make sure that what the current system does is actually well documented. And so I think this is another case where we can have better tools to help people be more productive in writing and, importantly, maintaining documentation that's in sync with the code. Okay, so this is my conclusion. The conclusion is that we really need to think about productivity over the entire software lifecycle. And this isn't just from the point in time when you start writing the code to the point in time where you kind of start debugging the code. It's really across the entire lifecycle of the software that you write. And the other thing is, as I've tried to highlight, I think there are areas in all of these places where we could invest to make everyone's lives easier and more productive. So with that, thank you very much.
Thank you. You've given so many things to think about. If there was 1 or 2 things that you could put on a wish list of you'd really like if people could do that now, I don't know if it's possible to narrow it down to that, but is there 1 or 2 really key things from the list you provided?
That's a really good question. Maybe I'll say a few things. One is that there are tools that have been developed already, say instrumentation-based debugging tools like the address sanitizers and thread sanitizers and such, that are very useful, but they just don't work very well for technical reasons on large-scale systems. So that's a sort of specific area where a little bit of investment could actually have a very large return. The other thing I'll say is that we are seeing in other contexts more intelligent tools being created, and I really think this is an important part of the future story. And I think this holds across things like refactoring tools. It applies to things like better code search engines and such. It applies to things like better synthesis tools to help people, translate their requirements into code. All of these places, we're seeing the revolution in artificial intelligence and machine learning combined with better database technology, better formal methods, better techniques to create productive tools, so that in other contexts, programmers can actually be much more productive than they are in the environment in which we currently work. And so I think one of the focus areas we're going to have over the next few years, or at least I hope we have over the next few years, is to start thinking about how we're going to take advantage of those advances in the scientific computing and high performance computing space.
All right, well, thank you so very much, Carol. And thank you for
well, thanks, Sarah. Thanks everyone else for listening.